Welcome to our video lecture on the structure of a crystalline solids. The members who work in a team to produce this video are Ahmad, I, Sulaiman, and May and Nagi. On this video, we are going to talk about these following points here. First, we will talk about learning objectives and proceed to talk as shown in the screen. Our learning objectives throughout the video will be to understand the difference between crystalline and non-crystalline solids. Also, by the end of this video, we will be able to understand and draw different types of metallic crystal structure. Then, we will be able to derive relationship between unit cell edge length of a crystal and the atomic radius of the atom present in it. We will also be able to compute the theoretical densities of different unit cell of crystal. We will be able to understand polymorphism and allotropy. We will also be able to understand and differentiate various crystal systems and Braggs lattice. We will also be able to draw point coordinates, plans, and direction within a cubic unit cell. We will be able to compute linear and planar densities. Finally, we will have a quick glimpse on what is X-ray diffraction and Bragg's law associated with it. Okay, so let's start with the difference between a crystalline and non-crystalline solid. The solid present around us can either be crystalline or non-crystalline. If the atomic arrangement on the solid is uniform and organized, then it is known as the crystallines. Let's look at figure A of a crystalline silicon dioxide. We can see how uniformly these atoms of silicon and oxygen are arranged in a hexagon. If the atomic arrangement on the solid is not uniform and are randomly arranged, then the solid is non-crystalline. You might have already thought of how non-crystalline atomic arrangement would look like by look at figure B. Yes, as seen in figure B, the silicon and oxygen atoms are randomly arranged in indefinite order and hence it is non-crystalline solid. So, crystal structure are those kind of atomic structures where atoms are arranged in a definite periodic pattern over a large atomic distance in a crystalline solids. They usually have long range order which will give rise to bigger grains. So, some of the crystal structures might also have relatively short range order which will give rise to form a solid with many tiny grains. The pictures of a crystal shown in the screen is a large crystal with long range order. See how perfect it looks on its geometry. Crystal structures are found in almost all the metals. Scientists have come up with amorphous metal with the superior properties, but almost all the metal have a crystal structure. Also, many ceramics and a few polymer have a crystal structures. The formation of a crystal structure depends on the processing technique, how rapidly a particular material is cooled. While studying about almost anything, we really need to know why are we studying it. It's so what we can be interesting about the topic. So why are we studying crystal structure? Why is it so important in material science? Crystallography is important because the properties of a crystalline solid depends on how atoms are arranged. Okay, so let's take an example of graphite versus diamond. Graphite is soft and dark, whereas diamond is hard and colorless. But both the graphite and diamond are made up of carbon. Why such a big difference? Well, it's because of the atomic arrangement of the carbon as shown in the figure on the screen. Look how the atoms of graphite are arranged and how the atoms of diamonds are arranged. We can see that the graphite carbon sheets are loosely bonded, while in diamond carbon sheets are tightly bounded in cubic crystal structure, which makes it one of the hardest substances in the earth. Very interesting. Knowledge of crystal structure helps us to dig on the structure and properties aspects of material science and engineering. Okay, now let's go briefly on what crystal structure is. Crystal structure are atomic hard sphere model. The atoms in a crystal are defined as spheres with definite diameters. Also, the spheres are thought to be touching nearest neighbor atom in an Atomic arrangement. Crystal structures are made up of crystal lattice and crystal bases. Crystal lattice are a three-dimensional array of points where atoms are located. So lattice is just the position where the atoms are located in a crystal. It is simply a marking to address where the atom sites in a crystal lattice. Crystal basis is the repeating unit of atom that can form the overall crystal structure. On the figure, the first one is the crystal structure. The second picture is the lattice point for the atom of the crystal structure. The third figure on the right is lattice basis. Therefore, if we have lattice point and basis, we can draw overall crystal structure. So, how lattice basis works as a condensed part of a crystal. Now, we know what the crystal structures is. Let's move on to metallic crystal structures. Metallic crystal structures are densely packed structures where atoms are closely packed with each other. There are three basic crystal structures in metals. First one is the body center cubic, where 3 is as central atoms on the body of the crystal as seen in the figure. Second one is the face centered cubic crystal structures that has atoms on the faces of the crystal structures. Third one is the hexagonal closed pack, where atoms are arranged in a hexagonal shape as shown in the figure. The few metals which has this structure is given below the crystal here. Wait, where is the simple cubic unit cell? It's not listed here because atoms on simple cubic unit core are not densely packed. As a result, metallic crystal structure do not have such crystal structure. Let's study this crystal structure one by one now. First, one is body center cubic. Body center cubic has 8 atoms on the corner and 1 atom on the center. The few metals that consist of BCC unit cell are iron, vanadium, niobium, chromium. On BCC unit cell, center atoms touch along the diagonal. The number of atoms present in BCC are 2. It has 1 center atom and 1/8 part of atom on each 8 corner of the atom, resulting in 2 total atoms. The edge length to ratio is A equal 4r/√3, where A is the edge length and r is the hard sphere radius. But how do we determine this relation? We will talk about it in next slide. First, let's consider the lower face of the cube and its diagonal is D. We can find the diagonal of the bottom face by applying Pythagorean theorems. D square equal A square plus A square equal 2A square. So taking root on both sides, D equal roots 2A. Now let's find the length of diagonal D dash. As seen in the figure, D dash joins the atoms on the upper right corner and the atoms on the lower left corner. We can again use the Pythagorean theorems to find this length. A square plus D square equal D dash square equal 4R square, as the D dash goes through full atoms on the middle and half of lower and upper atoms, so R plus 2R plus R equal 4R. By doing some algebra here, we get A equal 4R/√3. Atomic packing factor tells us how closely atoms are packed with each other in a unit cell. The formula of the atomic packing factor is total volume of sphere over total volume of cube. Therefore, if we know the volume of sphere, number of atom, and edge length of cube to determine total volume of cube, we can find atomic packing factor of a cube crystal. Here, APF equal total volume of sphere to the total volume of cube. We have Vs equal to 2 multiplied with 4 pi r cube over 3, Vc equal a cube equal 4r over square root of 3 to the power of 3. APF equal Vs over Vc equal 0.68. So atomic packing factor is 0.68 for BCC unit cell. Now let's move on to face-centered cubic unit cell. Face-centered cubic unit cell consists of atoms on the corner of the unit cell and 6 atoms on the 6th face of the unit cell. Some of the elements that show face-centered cubic unit cell are aluminum, nickel, silver, gold, and copper. On FCC crystal structure face atoms touch the corner atoms as seen here. Number of atoms present in FCC are 4. There are 8 corner atoms occupying 1/8 of atoms on all 8 corners. There are half of the atoms occupying all 6 faces. Therefore 1 from the corner and 3 from the face equal 4 atoms per unit cell. The edge to radius ratio is A equal 2r root 2, where A dash is the edge length and r is the hard sphere radius of atoms. We will talk briefly how this relation is derived in next slide. Okay, this is easy like we did on body-centered cubic unit cell. First, let's take the front face of the cubit. Let's mark the diagonal of the front face of the cube as D as shown here. This diagonal of the front face can be determined by using Pythagorean theorem, like we did on body-centered cubic unit cell. So, D squared equal A squared plus A squared equal 2A to the power of 2. D equals square root of 2A. D is equal to 4r larger than 1r from first atom, 2r from first atom, and 1r from third atom. Therefore, using algebra, A equal 4r over square root of 2 equal 2r square root of 2. Now, let's calculate the atomic packing factor of FCC unit cell like we did with BCC before. This will tell us which cubic unit cell is tightly packed and which one is loosely packed. APF equal Vs over Vc, where Vs equal total volume of sphere and Vc equal total volume of cube. Vs equal 4 multiplied with 4 by r cube over 3. Vc equal A cube equal 2r square root of 2 to the power of 3. Therefore, APF equal Vs over Vc. By doing some math here, we get APF for FCC equal 0.74. We can see that APF for FCC is greater than that of BCC.
This is Ahmad, and now I'm going to speak about the hexagonal clusterpack. The hexagonal clusterpack do not have atoms arranged in a cubic unit cell, but has an hexagonal shape. The top face has 6 atoms on the corner and 1 atom on the center. The arrangement is similar to the bottom face. On the midplane region, it has 3 atoms as shown here. Elements showing hexagonal clusterpack structure are titanium, zinc, magnesium, and cadmium. Let's calculate the number of atoms on HCP. HCP has 3 center atoms. It also has 1/6 of an atom on its 6 sides up and 6 sides down. Also, it has half of the atom on the upper and lower face. Therefore, total atoms are 3 plus 12/6 plus 2/2, which will equal 6 atoms per unit cell. HCP do not have APF, but has C/A ratio, which is mostly 1.633. Now let's compare number of atoms, packing factor, coordination number, and edge length to the radius ratio or the C/A ratio of the crystal structure we studied on this table. We can see that HCP has the largest number of atoms per unit cell. We can see APF and coordination number of FCC and HCP are the largest. The edge length of the to radius ratio and C/A ratio are each unit cell is different. The knowledge we have gained by studying various crystal structure help us to calculate the theoretical density of an atom. Theoretical density can be calculated by the formula ρ equals Na over VCNA, where N equals the number of atoms per unit cell, which we know from the table we had earlier. A is the atomic weight that can be easily obtained from periodic table. Vc is the volume of unit cell that we can calculate using the formula we derived earlier. Na is the Avogadro's number, which is 6.022 times 10 to the power 23 atoms per unit cell. Now let's use the knowledge to do some real-world calculation. We have taken this problem from example problem 3.4 from Callister. Copper has an atomic radius of 0.128 nanometer, an FCC crystal structure, and an atomic weight of 63.5 gram over mole. Compute its theoretical density and compare the answer with its measured density. Here, the radius of atom is given, which we can use to calculate the volume of unit cell, using h to radius formula that we had delivered earlier. Atomic weight is given. Since it is an FCC, we can find the number of atoms per unit cell using our table earlier, which is 4. Now let's plug all the value to the equation here. Rho equal n times A over Vc Na, which will equal to 4 times 63.5 over 2 root 2 times 1.28 times 10 to the power negative 8. That's times 6.022 times 10 to the power 23, which will equal 8.89 grams over cubic centimeter. The value from the literature is 8.94 grams over cubic centimeter, which is very close to the value we found here. Great. Now let's compare theoretical densities of various material category. Theoretical density of metal is greater than of ceramic. Similarly, theoretical density of ceramic is greater than the density of polymers. The composites have their densities in between them, depending on by what composition they are made up of. Why do metals have the high theoretical density? Why is this trend observed? It is because they have close packing and also have large atomic mass. Ceramic are less dense because they have less dense packing and are made from lighter elements. Similarly, polymers have the lowest packing density and they are made from light elements, like carbon, hydrogen, and oxygen. Therefore, this trend is observed. Now I'm going to start explaining the polymorphism and allotropy. Polymorphism is simply solid that have more than one crystal structure. If the polymorphism is observed in an element solid, it's known as allotropy. The characteristics of polymorphism and allotropy depends on temperature and pressure. But how? Okay, take an example of carbon. That shows how pressure causes this phenomena. Diamond is formed when there is high pressure, whereas graphite is formed when there is low pressure. This processing step changes the structure and properties and lead to difference in performance. Another example is iron. The iron is BCC at room temperature, but it's heated above 912 Celsius. The crystal structure changes to FCC till it reaches 1394 Celsius. Very interesting phenomena. As we have already gone through various crystal structure, we are already familiar with the unit cell. We will go more briefly here. Unit cell is simply small repeat entities. Most crystal structure are parallelepipeds, are prisms, and have 3 sets of parallel faces as shown in the picture. Unit cell can be translated along its edge to create the overall structure. The corners coincides with the hard sphere model. Therefore, unit cells are actually building block of crystal structure by virtue of its geometry and disposition of atoms within. There are various types of unit cell and they describe crystal systems. The crystal system are 7 in numbers. There are also 14 crystal lattice or brevis lattice as seen in the picture here. First one is triclinic, second one is monoclinic and has centered and simple crystal lattice. Third one is orthorhombic and has simple base center, face center, and body center crystal lattice. Fourth one is rhombohedral. Fifth one is tetragonal and has simple and body center crystal lattice. Sixth one is hexagonal. Seventh or last one is the cubic or isometric and has simple, body centered, and face centered. Note how the angle, edge length, position of atoms, orientation are different in all of these crystals. That makes each of them very unique. When we want to talk about something, it is important to address it first. Suppose we want to talk about particular atom in unit cell. How are we going to do so? This job is done by point coordinate system. Point coordinate system is used to address a position of an atom. There are 3 points coordinate system, Q, R, and S. These points coordinate system are fractional multiple of A, B, and C unit edge length. QA is a lattice position reference to x-axis. RB is a lattice position reference to y-axis. And CS is a lattice position reference to z-axis. Let's see example 3.5 in Callister. How are we going to locate the position P in the atom? Lattice position to x-axis equal 1 over 4 times A, which equal 0.12 nanometer. Lattice position to y-axis will equal 1 times 0.46, which equal 0.46 nanometers. Lattice position to z-axis equal 1 over half times 0.4, which equal 0.2 nanometer. Crystallographic direction has a line directed between 2 points or a vector. Steps to determine the directional indices are easy. We will first go through the steps and few examples. The steps are as follows. First, we should determine the coordinate of the tail, if it's either x1 or y1 or z1. Then we should determine the coordinate of the head, x2, y2 or z2. Then we have just to subtract head to tail, like for example, x2 minus x1 or y2 minus y1 or z2 minus z1. Normalize in terms of lattice parameter and smallest integer value. To clean it up, we should remove comma and enclose in square brackets. Negative signs should be replaced by bar above the number. And now it's a problem time. We have to draw a direction of 1, 1, 2. First, we need to divide the numbers by the largest integer. For our example, we have 1, 1, 2, so we're going to divide by 2. And then we will get half, half, 1. Then we to mark origin on the cube. Then move half on x, half on y, and 1 on z. The joint origin and the final point pretty easy to do. On this problem, we have to find the Miller indices of the direction in the cube. For this, let us find the head coordinate, which is 1, 1, half. Second, we will find tail coordinate, which is pretty simple, 0, 0, 0. Then we will subtract head tail, we will get 1, 1, half. Then we have to multiply with the largest integer to remove fraction. We will get at the end 2, 2, 1. Each crystallographic plane is unique inside a crystal structure. Therefore, if two planes are parallel to each other, then they will have similar Miller's indices and will be equivalent. Planes are also specified by 3 Miller's indices, H, K, L. Steps to determine a crystallographic plane are pretty simple. First, we have to determine the intercepts of plane and on axis in terms of A, B, and C. Then, we have to take reciprocal of the intercepts. Then we have to reduce to smaller integer values. Finally, we have to remove commas and enclose the parentheses, like in directions. Negative signs is replaced by bar overhead. Here we ask to find the Miller indices of a plane given. We will use the steps that we had discussed in the earlier slide. First, we will find the intercepts on x, y, and z axis, which is 1, 1, infinity. Second, we will do the reciprocal, which is 1, 1, 0. We now reduce to 1, 1, 0 and then enclose in parentheses without comma. Remember that if we had a negative sign, we had to place it above the number. Here we get another problem. We are asked to draw 1, 1, 2 plane. Here we'll just follow the reverse order of our steps. First, we need to take the reciprocal of the numbers, which is 1, 1, and half. Then we'll mark 1 on x-axis, 1 on y-axis, and half on z-axis. At the end, we have to connect these points and shape the plane.
My name is May, and we will go through linear and planar densities quickly. Linear density is the ratio of number of atoms centered on direction vector to the length of the direction vector. The formula is LD equals number of atoms centered on direction vector over the length of direction vector. Planar density is the ratio of number of atoms centered on a plane to the area of the plane. The formula is PD equals number of atoms centered on a plane over area of the plane. Since we already have studied the crystal geometry, we can easily calculate the densities using the formula above. The unit cell are translated to form a single crystal. Single crystals are anisotropic, that means the properties vary with direction. For example, the modules of elasticity in BCC iron 273 GPa in diagonal, but 125 GPa in edge. Look how the atoms are arranged in the crystal. When there are numerous single crystals, then it is known as polycrystal. The image here shows polycrystal with two single crystals. Properties of polycrystal may or may not vary with direction. If grains are randomly oriented, then they are more isotropic. When polishing and grinding, if grains are not textured, they are isotropic. In amorphous solids, atoms are randomly oriented. Remember, the first slide of silicon dioxide, the atoms were randomly oriented. Amorphous solids have no definite crystal shape. Glass showing glass transition temperature are amorphous. Now, let's learn something about X-ray diffraction and how crystal structure is studied. Diffraction is a phenomena that is consequence of specific phase relationship established between two or more waves that have been scattered by the obstacles. This phase relationship between the scattered waves, which is determined by the difference in path length, is important in the study of crystal structure and to determine the interplanar distances. So, why do we consider X-ray and not microwaves or radio waves? It is because diffraction grating must have spacing comparable to the wavelength of diffracted radiation. A wavelength of X-ray and spacing, the distance between parallel planes of atoms, closely match with each other. Here are two rays that are incident on the surface of the crystal structure, beam 1 and 2, having wavelength lambda. They will strike and get diffracted by the atoms of the crystal as shown here. When they get diffracted, the rays too have to travel extra distance, SQ plus QT. This distance is helpful to determine the interplanar spacing. The change in the wavelength can also be measured and used in Bragg's law to study crystal structure. BCC has these first 6 reflection indices. Similarly, FCC and SCC has these first 6 reflection indices of its planes as seen in the table here. This is diffraction pattern seen in powdered lead. By looking at the diffraction pattern and looking at the reflection indices, we can say that it has FCC crystal structure. In this video lecture, we understood the difference between crystalline and versus non-crystalline solids. We also understood the different types of metallic crystal structure. We learned how to derive relationship between unit cell edge length and atomic radius. We computed theoretical densities and compared it to experimental value. We understood polymorphism and allotropy. We also understood various crystal systems and learned how to draw point coordinates, planes, and direction within a unit cell. We learned how to compute linear and planar densities. At the end, we went briefly through X-ray diffraction. The video lecture has served as a source to revisit and re-examine the components, and we hope it was helpful for you to understand the structure of crystalline solids. Each of us worked diligently and carefully to produce this work. We thank each of us for being supportive and motivating throughout the project. These are the sources we used to make the video lecture. We are thankful to our professors, Dr. David Estrada and Dr. William Knowlton, for giving us this opportunity to make this video lecture. We enjoyed making it. For questions and comments, you can email any of us at the address shown here, and we will be happy to talk to you. Thank you for viewing our video lecture.